Thank you for that over generous introduction. So I'd like to thank the organizers, especially Pinaki, for giving us an opportunity to talk about our recent work. Um, and it's a pleasure to, of course, see old friends like Professor Chiang also on this audience. Um, so what I thought I will talk about could be like one aspect of our work on financial markets. But before I get into that, I thought I would just spend a little time on the broad philosophy of why physicists like us have got into, like the world of financial markets, not as speculators, but more as, people who are interested in understanding how markets work. So a few years back, along with two economist colleagues, I was involved with compiling a special issue of this journal, European Physical Journal Special Topics, where very ambitiously we gave the following title to our special issue, Can Economics Be a Physical Science? In retrospect, I think it might have offended a few of the economists whom we had invited to contribute articles to this issue that, why on earth would we want to ape physics as our model? But interestingly enough, all the economists we asked actually graciously agreed to contribute to this issue. And it was one of the very few forums I have seen in which we had roughly equal number of physicists and economists writing on what is their perspective on whether you could have economics develop into a subject which kind of has similar associations that we have with physical sciences. In particular, the one question that engaged many of our contributors was the issue of whether there are universal properties, what we would call laws in physics, whether there are anything like that in economics, or whether it's even meaningful to talk about laws in economics. One particular example of laws that, what kind of laws we might expect in economics that I often quote when talking to economists uh, is something that I took from financial markets. And this is something that is largely coming out of the work of the Boston group of econophysicists, originally led by Professor Gene Stanley, where although the first evidence of such a law was actually obtained by Thomas Lux in Germany. So what is this law? Essentially, it argues that if you look at price fluctuations of, let's say, a market index or that of individual asset prices, then the distribution of these fluctuations appear to obey some kind of an universal behavior. In other words, whether you look at, let's say, asset A or asset B, whether you look at financial market X or financial market Y, or whether you look at period T or whether you look at period T prime, essentially the distribution nature would be identical. Now, you might say, well, isn't that a cop out? I mean, it's not really a deterministic law as in physics. It's more like a statistical law. Well, unfortunately, the individual entities of markets and indeed of any social sciences tend to be much more unpredictable than the collective as a whole. So therefore, statistical laws would be what we might reasonably expect from such systems. So what this law, so to say, says is that if you look at the return of the asset price, so let's say you are calculating the logarithmic return. So this is, I'm sure most of you are familiar with this, but just in case some of you may not be familiar with this particular definition, it looks at the difference of the logarithm of the price of a particular asset at two successive time instants. And so it's a measure of how much the price has changed over a small time interval. You could, of course, use other measures. So, for example, you could just look at the difference in the price itself without getting into log. Unfortunately, that would start depending upon the unit in which you measure the price. And we would, of course, ideally like to make the measure unit independent. You could also look at the ratio of the price at two successive instants. And indeed, if the time difference is very short, you can show that this definition becomes identical to if you're just using, let's say, ratio of two prices. Whatever be it, there are some very nice properties associated with a log return, which is why it's so widely used as a measure of price fluctuations. So if you look at how this behaves for a typical asset, so in this particular case, I'm looking at the price of Reliance as listed at the National Stock Exchange of India over a period of about 12 years. Then the price itself has behavior similar to that of a random walk. But if you look at the return, which is the price change or the increment, you can see that that has a very peculiar looking trace, which becomes very apparent once you start comparing it with Gaussian noise. In particular, you notice that you have extremely large fluctuations occurring remarkably often, which you wouldn't expect had this been a pure Gaussian noise. Now, this may surprise people, this may not surprise people. So if you're a believer in the random walk nature of price movements in markets, you might be surprised. But on the other hand, if you say, well, I'm a follower of Mandelbrot, and he had back in the 60s shown that cotton prices clearly have a very different behavior from Gaussian. So what's the surprise and so on. So might surprise, might not surprise. I'm not getting into that. But what is interesting is that if you actually try to characterize this distribution, you would find that it follows a very precise description. The tail of this distribution follows what is known as a power law. So there's an algebraic scaling of this fluctuation, which essentially goes as the magnitude of the fluctuation raised to some power. And in fairly classic paper, which was published in the mid-90s, Professor Stanley and others claimed that this exponent would almost always be around 3. And this essentially gave rise to the famous or infamous, depending upon your perspective, inverse cubic law. So this said that if you look at the distribution of fluctuations of, let's say, an asset, or for that matter, a market index, then provided you are not looking at too long a time interval, you would find that it would follow this very characteristic algebraic scaling, or the tails of the distribution would follow this very characteristic algebraic scaling, which is an exponent of 3. And this would be true regardless of what index you look at, what asset you look at, whether you're looking at the New York Stock Exchange or the London Stock Exchange or the Paris Bourse, or your favorite market, or whichever country you're interested in. So you could be interested in US markets, you could be interested in Latin American countries, whichever. Now, notice that I have said that this is valid over an interval of about a minute to a day. A minute means you can go down to almost like tick size. But why doesn't it remain valid for longer time intervals? Well, for one, if you notice here, the exponent value is such that this is going to be subject to the central limit theorem. So in other words, if you look at sufficiently long intervals, if you aggregate enough of these fluctuations, eventually it's going to converge to a distribution which would be well described by a Gaussian distribution. So in long term, it would essentially follow a Gaussian distribution. So from that point of view, Behavior and his later followers were not incorrect. If you look at a sufficiently long time interval, it would eventually become essentially a Gaussian, or it would be well described by a Gaussian process. But at short time intervals, it's definitely showing remarkable deviations from the Gaussian process. Now, I mentioned that this has been shown to be, remarkably universal in the sense that different people have shown it to hold true for various kinds of markets, various countries, various asset classes, and so on. So in, just about 8 years back, we kind of were interested whether other kinds of assets, not just financial assets of the kind we're used to, but maybe, let's say, virtual assets like Bitcoin would also follow this behavior. And probably not surprisingly, we found that it does follow an algebraic scaling. However, the exponent is not 3, which is what the inverse cubic law would expect you to believe, but it's actually closer to 2. And we kind of came up with this term called inverse square law of for the Bitcoin. We also made kind of a prediction in this article that possibly this is a signature of the development of Bitcoin, that eventually it would converge probably closer to 3. So if you come back and look at at a time when Bitcoin has become a very accepted class of asset, which a lot of traders deal with, maybe it would come closer to 3. But that was purely a speculation, and to some extent based upon our agent-based models for how financial markets eventually give rise to this inverse cubic law. But that's a topic for a different time. So I'm particularly enamored by this inverse cubic law because that's kind of provided the entry point for me into econophysics. So my former mentor, Professor Bikash Chakraborty, whom several of you might have heard of, or may have heard his talk, had been like trying to get me into econophysics for a fairly long time, but somehow I never felt the urge to get into it. But in about 2006, I and my first PhD student, Rajkumar Pan, we're looking at a paper that had just come out from Stanley's group, which claimed that somehow Indian markets were special and it didn't follow inverse cubic law. And looking at the kind of the way the paper kind of made this claim, I didn't feel that it was a very well-founded observation. So we thought let's try this. It will, if nothing else, it will provide us some fun, some diversion, and also a kind of training exercise for what do these econophysicists do. And so we took set of data that was very graciously given to us by a colleague of mine who worked with Indian financial markets at that time. So that's one of the benefits of working in an institute with people working in all sorts of different areas. So in the Institute of Mathematical Sciences, the name might seem to suggest that we are mostly mathematicians, but actually the majority are physicists. And even among the mathematicians, there are quite a few who does really fun stuff, like looking at the geometry of origami tiles and so on. So one of my colleagues, who's Krishna Madali, who's retired since, was working on the National Stock Exchange and also the Bombay Stock Exchange, and he was already working with this data set, and so he said, sure, if you're interested, why don't you take a look at this data? And so we started computing the return distribution, with a lot of care, and we found that contrary to what Gene was claiming at that time, the Indian market indeed followed this same algebraic scaling with an exponent of 3. And so therefore, at least from the point of view of distributions, there seemed to be very little difference between a developed market like the New York Stock Exchange and an emerging market like that of India. So if you compare them one on top of each other. So here, for example, I'm plotting the cumulative distribution of the price returns for the National Stock Exchange of India and the New York Stock Exchange on top of each other. Only for the negative tail at the very extreme end, you see a small difference. And so it looked to us that indeed the inverse cubic law is quite robust, and definitely India is not an exception, even though the paper claimed that because of its developing status, maybe that's why it's not following this inverse cubic law. And we started getting interested in this question of what might be the difference between a developed market like that of New York Stock Exchange and an emerging market like that of India. And so that's how we got into this whole question of how do you characterize the structure of interactions between different asset classes of a market. And at about the same time, Kim and Jeong were doing a similar exercise for the New York Stock Exchange. And we were very much inspired by their work. So we asked ourselves that, if you look at the Kim and Jeong's work, they are essentially showing that the different sectors, the different sectors such as insurance, energy, healthcare, technology, all of these asset classes belong to these different sectors, kind of behave independently of the others. So if you look at how the prices of these different assets are moving up and down, then the assets belonging to the healthcare sector seem to be much more correlated with each other than, let's say, with the assets belonging to, let's say, the energy sector. So there are these kind of strong intra-sector interactions which seem to be holding them together. So we decided to see whether this holds true for an emerging market, and in particular we chose the Indian financial market. And just to give you a preview of what's to come, essentially we found that there were similarities as is shown here. So for example, you see that the infotech, the pharma, and a large cluster of which the petro stocks are kind of a major component, they do actually emerge out of our analysis, but certainly it's not as clearly demarcated into as the US market. And therein lies where we took the story next. But to step back and basically tell you what exactly we were doing, so we asked ourselves that how do we understand the network of relations between these different stocks. So as physicists, what we had in mind was this picture of Brownian motion of particles. So I'm sure all of you are familiar with this whole history of Brownian motion. So Robert Brown, a botanist, was the first to describe the motion of small pollen particles suspended in liquid. And it appeared to him that these were essentially alive. But careful experimentation made him realize that these are completely inert. And so kind of he did experiments even with clearly inorganic substances like soil and so on suspended in liquid. And he found that as long as they are of the same size, they would all show similar erratic motion. And so the question was, what's making them move if they're not live? And of course, the answer eventually was given in a wonderful mathematical exposition by Albert Einstein, where he showed that this is essentially because of Brownian motion. So what's happening is that each of these pollen particles are essentially being hit by millions of air molecules from all sides. And occasionally there would be more air molecules which are hitting it from this side than from this side. And so there will be a net motion which is going to be directed in this direction. But sometime later, there would be a net motion in another direction because there would be more particles which would be hitting it from this side than from this side. And so there would be an unbalanced force which will be taking it there. And so the picture I had in mind was that, you have all these people in the market, and for that matter, automated algorithms which are buying and selling various asset classes. Now, obviously, the motive force of these market is provided by these agents. But let's say we are unable to observe the actual actions of these agents. But instead, what we see the result of their actions, namely, are more people buying than, let's say, selling a particular stock, or more people trying to sell a particular stock than them buying it. As a result of this, the prices are going to go up and down. And so what we are seeing is essentially the effect of all this traders' behavior rather than uh, the actual buying and selling itself. Now, as a result of this behavior, you could have different asset classes moving in a synchronous manner, or they could be moving in opposite directions. And by looking at the behavior of these asset classes against each other, we can get some kind of a gross or a macroscopic view of how the market dynamics is evolving over time. And so what we decided to do was essentially measure how similar these price movements are. And for this, we looked at cross correlations. Now, you might argue, hold on a sec. I mean, this is basically a linear measure. I mean, wouldn't you be better off by using a nonlinear measure like mutual information? Well, we did try that. And for whatever reason, we found that financial markets are actually fairly well analyzed by just looking at linear cross correlations. You can do normalized mutual information or similar measures, but it turns out that it doesn't really add anything significant. But that's not true, for example, for currency markets, which clearly mutual information actually can give you some very different behaviors. All right, but that's slightly of a diversion. So let me go back to what I was saying. So technically, what we did was that we looked at the cross correlation between these returns that I mentioned to you, which is essentially a measure of price fluctuation. So we are asking, if I look at asset class I or asset I and asset J, are the fluctuations similar? That is, do they have the same sign? Do they have a similar magnitude? Or how dissimilar are they? And in order to compare between the Indian and the US markets, we looked at both data sets from the National Stock Exchange as well as the New York Stock Exchange over roughly the same period. That is from January 96 to May 2006. There was some small difference in the number of working days because the kind of the days on which the markets are closed in these two markets, of course, differ because they belong to very different countries and cultures. But roughly we tried to make sure that there was some kind of a parity between the two. So if you just use the correlations to try to and then try to build some kind of a relation between them. So for example, many people use this minimal spanning tree where you connect up all the n stocks into a network with just n-1 links. Such that the total sum of the distances, and here the distance is basically related to the cross correlation using a measure like this, which has all the properties of a metric. So the idea is that you want to link it all up such that the total sum of the distances between each pair of these assets is minimum. So you want to minimize the total sum of these distances. So this has actually been done for many markets, like Professor Kimokaski's group has done it fairly long time back, and others have also done it, including Professor Mantegna's group and so on. So you could do something similar, but drawing any conclusions from this is somewhat dangerous. The reason for this is that if you look at an infinitely long time series, then cross correlations would typically give you a genuine result. So for example, if it turns out that these two things that you're looking at really don't have any correlation, you expect the cross correlation to be zero, right? Now, if they were of infinite length, you would indeed get zero. But if you look at finite time, then just through stochastic fluctuations, you can actually get a finite result. And so this is a problem when you're trying to use raw cross-correlation data to construct minimal spanning trees like this. So many of these connections could just be spurious. They could be just be a result of stochastic fluctuation because you're looking at short time series. And so somehow we need to figure out which are the links which we could trust, which are clearly not an outcome of just stochastic fluctuations, and which ones are kind of has to be treated with a little bit of suspicion. So for this, we decided to look at the spectral properties of the cross-correlation matrix and compare these properties with those of a random surrogate. So how do we create this random surrogate? So one of the easiest ways is you take these different time series of the various asset price returns, the asset price fluctuations, and then you randomly permute them. You scramble the data. So if you randomly scramble each of this time series in turn, you still have the same distribution because the numbers are all still the same, but the sequence is completely different so that you have destroyed any possible significant correlation that there might have been between them. So what we did was we created ensembles of random surrogates by taking these return time series of the different assets and randomly permuting them. So we decided to compute the eigenvalue spectrum of the empirical cross-correlation matrix as well as that of these randomly shuffled surrogates. And here we could actually use a very elegant result from random matrix theory known as the Marchenko-Pastur distribution, which essentially tells you that if you have a matrix, so these classes of random matrices are known as Wishart matrices. If you are looking this up, they would be falling under the class of matrices known as Wishart matrices. So this is a wonderful result for such classes of random matrices. And we could actually compare the matrix with that of the randomly shuffled surrogate. And we could compare both of this to what we would get from this theory given by the distribution form of the Wishart matrix, namely the Marchenko-Pastur law. And you can clearly see that while the randomly shuffled surrogate agrees beautifully with that of the theoretical result given with the Marchenko-Pastur law, the empirical distribution has significant deviation. In particular, the largest eigenvalues, several largest eigenvalues of the empirical distribution of the eigenvalues of the cross-correlation matrix have significantly larger numbers than what you would expect from the Marchenko-Pastur distribution. So for example, the largest eigenvalue of the empirical cross-correlation matrix was 28 times larger than the largest eigenvalue of the that we would expect from the Wishart matrix. And there are also quite a few intermediate eigenvalues. That is, they are not the largest eigenvalue, but they are also clearly not belonging to this bulk of the eigenvalue distribution, which is well described by the Marchenko-Pastur distribution. So if we are trying to use this now to, in some sense, denoise the network so that we can try to see which parts of the network are essentially a result of noise and which parts are a result of genuine interactions or genuine cross correlations. There is one problem that we have to first confront, and which is that oftentimes you will notice, and this is especially true in, for example, emerging markets, that if you just do analyze the raw cross correlations, you would feel that they are highly correlated. Almost everything is correlated. And that's because, as we figured out, the largest eigenmode essentially dominates all the other eigenvalues, okay? All the other eigenmodes. And what's this largest eigenmode? It's essentially the market mode. It's basically the global signal which is moving the market as a whole. Okay. So let's say the Prime Minister comes on TV and announces, some big change, and next day all the stocks tank. Okay. It doesn't matter which sector they are in; they are just all going to go south. Now, suppose you're interested primarily in looking at how stocks within a particular sector interact with each other. So this kinds of global signal is kind of a big distraction, right? Because they tend to mask out, their effects are so great that they tend to mask out all this subtle interactions that are there of stocks belonging to the same sector, or which essentially respond to the similar information. So we wanted to somehow not only get rid of the noise, but also get rid of this distraction of this very large global signal. And so we took help of something that anyone who has taken a basic course on linear algebra would know. Essentially, it's a way of rewriting a matrix in terms of sum of product of the eigenvalues and eigenvector. So you look up linear algebra 101 course, and you see that you can write down any matrix C as essentially a linear combination of products of its eigenvalues with the corresponding eigenvectors transpose and the corresponding eigenvector. And so essentially we use this idea that we can write down the empirical cross-correlation matrix as essentially composed of three parts. So there is this, the largest eigenvalue times the product of the transpose of the largest eigenvector and the largest eigenvector itself. So that would essentially give us the component of the correlation matrix, which corresponds to this effect of the market signal, the global signal, which overall the market is responding to. There's also the random component, which is essentially everything which falls within the random bulk, which is well described by the Wishart distribution or the Marchenko-Pastur distribution. So all eigenmodes which essentially fall within this bulk, I would basically take a sum of those quantities, and they would actually give me the random component. And in between, so eigenmodes whose eigenvalues are neither the largest eigenvalue, nor do they belong to this random bulk well described by Marchenko-Pastur, that this intermediate eigenvalues would give me the sectoral contribution of the cross-correlation matrix. So essentially, if I just consider this part, rejecting the largest eigenmode and the eigenmodes which fall within the random bulk, I would essentially have a description of how the interactions that dominate at the sectoral level essentially result in interactions between different assets. So we use this idea in the empirical cross-correlation matrix that we got from the Indian market, and just by visual inspection we could find that there were 5 intermediate eigenvalues which essentially clearly were separated from the random bulk and were also not close to the largest eigenvalue. And well, it turns out that it's actually not very significant, even if you make a small mistake, because most of the time the mistake you'll make is probably you would mistakenly pick up eigenmode which properly speaking should belong to the random bulk. But it's also true that this would be the smallest of all the eigenvalues, and so would have the lowest contribution to this sectoral cross-correlation matrix. So, so now that we have essentially a cross-correlation matrix which is obtained by essentially denoising it, getting rid of all the components which could have arisen from simply stochastic fluctuations, and also we have gotten rid of this largest eigenmode, which essentially would mean that we don't have this blinding light of these global signals to which all the kind of stocks are responding to. How do we actually get to visually represent the interactions between these stocks or assets? So we used a very simple kind of measure. We simply said that, look, if the value of the correlation matrix is greater than some threshold, then we would say that a strong interaction exists. So we would say that these two assets are linked, and it will be zero otherwise. And then we asked, okay, so suppose we vary this threshold, how does the number of isolated clusters change over time? So we found that there was an optimal cutoff value at which we had the largest number of isolated clusters, namely 3. And so we decided to use this to visualize the market. And out popped 3 sectors. So we had one sector which was clearly dominated by information technology stocks. So all the black nodes that you see over here are the infotech stocks, and the ones which are kind of blue are the telecom stocks. There are a few outliers, but they are just very few in number. So similarly, this one is clearly dominated by all the pharmaceutical stocks, the only exception being this FMCG stock over here. And the third one, the largest one, cluster, was essentially a mixed bag, but here all the petrochemical stocks kind of clustered together. Now, this clearly was quite a bit different from what one would have expected from looking at Kim and Jeong's paper, where they analyzed the New York Stock Exchange, where they had identified actually 9 very distinct sectors. And one of the questions that we got asked in many conferences when we were presenting this is that why this difference? So essentially, our understanding of it was this, that it kind of clearly showed the difference between 2 ways in which you can get correlations. So you can get correlations because you are essentially not interacting really with each other, but just responding to a common signal, or you could be correlated because you are actually strongly interacting with other stocks. And in our mind, the correlation that we're seeing in emerging markets were primarily because they were responding to global market-wide signals. There was a relative lack of sector identity, so relative lack of interactions between stocks belonging to the same sector. Whereas we expected that in mature markets, sectors would stand out because now there would be very significant sector-specific dynamics. So once I was giving this talk in one of the Nikkei conferences, and I was suggesting that National Stock Exchange of India is very, very similar to New York Stock Exchange in terms of the distributions, in particular the price fluctuation statistics. But the moment you look at interactions, you clearly see a difference with developed markets. And it's possible that this is the signature of the stage of development that a market is in. So maybe as markets develop, they would tend to become more and more clustered, and these clusters would emerge, more and more clusters would emerge with distinct sector identities. So there was a member of the audience who immediately challenged me that why don't you do this study sometime later and show that this is indeed the case, that as the Indian market develops, clearly more and more sectors are developing. And so I remembered this comment, and so a few years back in 2016, I had a summer intern working with me, and I kind of told him that, look, there was this thing that we did some years back, and so why don't you take a look at how the market has developed since then? And sure enough, he found that while the information technology and the pharma sectors continue to retain a distinct character, other clusters also emerged, in particular the finance and the industrial sectors. So here we are showing it in a very different visual representation. We are using a dendrogram, but the colors essentially represents the different sectors. And here you can see that all the finance stocks have clustered together, all the technology stocks have clustered together, all the industrial stocks have clustered together. And in addition, you also have the pharma sectors. So the pharma sectors are kind of, there are 2 groups in which they have clustered. So there's one here and one here. So the other suggestion that particular question planted in our minds was that while in the case of the Indian market, we have to clearly wait for the future to see what's going to happen, how it's going to develop. how about if we look at, let's say, the data from developed markets, in particular data coming from the time when they were still developing, and can we see a clear difference? So the market that we had in mind was, of course, the US market, and in particular the New York Stock Exchange. And for a while, we had trouble getting hold of the data, but eventually we were joined by this economist collaborator of mine, Anindya Chakrabarti, who kind of, gave us access to this database where we could actually look at how the New York Stock Exchange developed from 1925 onwards. And very soon we started asking the question, apart from this question of, does clustering increase over time? We started asking this question that, can we actually see any clearly discernible signature of, remarkable changes in the markets from the way the structure of interactions are changing? In particular, if we look at the Great Crash, and the data set was from 1925, so clearly the Great Crash was included in this data set. Could we see anything interesting happening in the structure of interactions during the events leading up to the Great Crash? And of course, back in our mind was also the fact that we had this kind of event in 2008, which was almost as bad, and if not, according to some economists, worse than the Great Crash. And so, could there be similarities in the way the market structure responded to these cataclysmic events? So essentially our goal shifted from just looking at clustering, merely looking at how clusters change over time, to asking, could this provide robust signatures of systemic crisis? So what we did was we looked at essentially the New York Stock Exchange data for the period 1925 to 2012, and we split the data into 85 overlapping periods of about 1,000 days, and we started looking at how the behavior of the cross-correlation matrix over these 85 non-overlapping periods change. So essentially, we wanted to see how the structure of interactions are actually changing over this 85 overlapping periods. So, as I mentioned to you before, we kind of separated out the sectoral contribution. So if you just look at the distribution of the correlation matrix elements of this sectoral cross-correlation matrix, you already find some very interesting behavior. So for example, if you plot the distribution of these sectoral cross-correlation matrix elements, you find that as you go from, let's say, 1920s to 2010s, you find that the nature of the distribution is clearly changing in some kind of indicative way over this period. And the fact that you have very large values of positive correlations emerging in certain periods is kind of indicative that at certain points of history, there's extremely large or abnormally large correlation between stocks. And so we wanted to understand this, much more quantitative way. And so what we did was we reconstructed the interaction network. So as before, we kind of put in a threshold, but in the meantime, my student Chandrasekhar, who was working on this, kind of came up with a very interesting idea. So he said that, look, why don't we, instead of just arbitrarily picking a threshold which kind of gives the largest number of clusters, why don't we use the following criterion, that if the value of the matrix element is greater than 3 times the standard deviation of the distribution of the matrix elements of the random component of the cross-correlation matrix, we would consider that as significant. So that was a brilliant idea, because the cross-correlation matrix corresponding to the random matrix elements, not surprisingly, follows a Gaussian distribution. And so if you take a value which is greater than plus minus 3 sigma of this random distribution, essentially what you're saying is that there's less than 1% chance that this would have the same value as that belonging to the random component of the cross-correlation matrix. So clearly, you can have some statistical significance, some clearly marked statistical significance associated with it. And so here I'm showing you just two snapshots of the cross-correlation matrix we use to generate interaction networks. So this corresponds to the period 2002 to 2006, whereas this corresponds to 2008 to 2012, where the Great Recession was occurring somewhere in the middle of this period. And you can clearly see the difference, right? So now you have a lot of things getting interacting very strongly with each other. So let me point out that the blue essentially correspond to positive interaction and the red correspond to negative interaction. And so here it's you can clearly see that there are strong sectors developing where within sector you have mostly positive interaction. Whereas here almost everything seems to be connected. There are blue and there are red and so on. And so we started asking, okay, can we use some kind of network metric to come up with some good measure of what exactly is going on here? What is changing as you have cataclysmic events unfolding? So we saw that almost all network metrics we looked at, like connection density, negative edges, clustering, all of them tend to increase during crisis periods, or which we know to be crisis periods, like during the Great Depression and during the 2007 crisis. In particular, when we looked at the core of the network, so some of you may have heard of the terms core periphery net. Some of you may be very familiar with this, but for those who are not familiar with the idea of core and periphery of a network, the understanding is that many networks have the following structure, that they have a clearly marked core where the nodes are very densely interconnected with each other. And you have a sparsely connected periphery where there would be nodes which have relatively few links, and they would not really be connected to each other, but mostly with some members of this inner core. And so we were interested to see whether these kinds of networks have some kind of a core periphery organization. So we were kind of arguing that, look, here clearly this both of these cases there is an inner core of the network, but the size of the core is clearly very different. So here there is a small inner core, whereas here kind of the core size increases radically. And sure enough, when we looked at the core size distribution, so here, for example, I'm showing you the visual representation of what the innermost core, the intermediate cores, and the outer periphery of the New York Stock Exchange look like. So for example, so basically these are multi-level pie charts, and you would notice that if you look carefully that there are 4 levels or 4 rings of this pie. So so there's this innermost core which is located at the center, then which essentially corresponds to the inner quartile or the inner 25% of stocks which are most densely connected. And then you have the the intermediate quartile. So the second ring has 25 to 50% of the innermost stocks. Then the third ring has 50 to 75%, and then the fourth, the outermost periphery, has between 75 to 100%. Now, they are also distributed in terms of the sectors that they belong to. So the color code is given over here. Now, you'd notice that precisely during the Great Crash, you had the inner core suddenly increasing in size. And post-crash, it kind of reduced. It's still not gone down to pre-crash levels, but it's still pretty small compared to what it was during crash. And we found that this is also true during the 2008 crisis, 2007-8 crisis. Clearly, the innermost core became big and remained quite large for a significant amount of time. So all of this was telling us something, but we didn't know quite what, until Chandrasekhar hit upon this idea of looking at structural balance. So what's structural balance? So this is an idea that was given by the cognitive or gestalt psychologist Fritz Heider way back in 1946. So he said that, suppose you're looking at relationships between mutual acquaintances. So let's say you have 3 friends, or three individuals. Let's say Om, Pradeep, and Zina. You can have different kinds of relations between each pair. Okay? So, for example, you can have Om and Zina are friends, and so the link between OX is positive. And Pradeep and Zina could also be friends, so the PX link is also positive. But then, let's say Om and Pradeep are enemies. They're rivals for the affections of Zina, and this will result in a tension, right? So Hydra basically said, look, there could be mutual relations which are balanced. That is, if those relations exist, there is no tension, inherent tension in the uh, overall system. But there are also antagonistic relations which kind of result in tension, right? So if everyone hates the guts of each other, that's also results in tension. Or if two people like, or like if two of the pairs are affiliative, but the third one is antagonistic, that also leads to tension. And Hyder's claim was that essentially this will be resolved by, for example, here, if Pradeep, Om, and Zina are all mutual rivals, eventually Pradeep and Om would probably form a pact to, become enemies of Zina. And so this will result in a relation like this. So this is, there's always a tendency to go from a tension or an unbalanced situation to a balanced situation because of this adage that, like friend of my enemy is my enemy or enemy of my enemy is my friend. Now, this idea was actually taken to a very mathematically sophisticated level by two graph theorists, Cartwright and Harari, in 1956. And they showed that in order to show that a graph or a network is balanced, you don't need to show all possible structures like rings of 5 nodes or rings of 4 nodes. You only have to show that all the constituent triads are balanced. They further showed that if the network is balanced, you can always divide it into two communities such that each of these communities would have all edges within them positive, but all edges, all links between these two communities would be negative. So in other words, something like this. So here, this is a perfectly balanced situation because within this community, all the links within the members belong to this community are positive. All the links belong to this community are positive, but the links belonging between these two communities are negative. Now that has remarkable dynamical implications because this would suggest that all the elements here would be synchronized, all the elements here would be synchronized, but these two would be out of synchrony with each other. So this, of course, has been applied to, for example, very interesting, context, like, for example, looking at international relations. So there's this remarkable work done by Sid Redner and collaborators on whether, decrease in balance eventually led to the First World War. So they basically analyzed the relations, the mutual defense pacts between the various participants in the First World War and showed that there was an increasing tension in terms of structural balance as First World War approached. And then, as a result of the war, all these tensions were resolved. And as physicists, we were particularly interested in this because structural balance actually corresponds to a situation of no frustration. So frustration, as many of you may know, essentially corresponds to a rugged energy landscape where the system gets trapped into any one of a large number of local minima, whereas a balanced network would have a smooth energy landscape. So Chandrasekhar started looking at frustration in these kinds of networks that we constructed. And sure enough, he found that precisely in the time of the Great Crash and during the 2007-8 crisis, you have unbalanced triads emerging in the network. So this led us to this remarkable conclusion that loss of structural balance is a very good indicator of systemic crisis. Essentially, we are arguing that what is happening is that there is a transition from one kind of dynamics to another kind of dynamics. And during this transition phase, we see a loss of balance, which essentially marks this onset of systemic crisis. So I'm sorry for slightly running out of time, but I'm at my last slide. So to conclude, let me just point out that we are essentially engaged in this remarkable enterprise where we are trying to see whether, as in physics, we could actually tease out universal laws for economics. And of course, the wonderful system that is a gold mine for mining for these kinds of laws is financial markets. And so Not surprisingly, financial markets have proved to be a very rich source of many universal features. In particular, we have been looking at this distribution of price fluctuations. Uh, but we also find that while markets do not significantly differ in terms of distributions, the networks that describe how the movements are correlated can actually alter very much depending upon the stage of development. And what we found was that by looking at the qualities associated with these networks, in particular, the presence or absence of structural balance, which in terms of physics we can also call frustration, we can actually see that frustration indicates systemic risk, eventually leading to severe economic crisis. So I'd like to conclude by thanking generous funding from the Department of Atomic Energy, which has, for a long period funded our Center of Excellence in Complex System and Data Science, without which we couldn't have been able to, do much of this work. I'd also like to acknowledge my collaborators in this work. So Rajkumar Pan, as I mentioned, who was instrumental in, getting into this whole business of analyzing price fluctuation distributions and showing that inverse cubic law is indeed also holds for India, but also more importantly, who was the prime mover in doing the first cross-correlation analysis of the Indian financial market. Anindya Chakrabarti, my economist collaborator, who is a faculty member at the Indian Institute of Management, Ahmedabad, and Chandrasekhar, who in fact just graduated last year and is currently a postdoc at Boston, without whom this work would not have been possible. So I'd like to thank you for your attention, and I'd be happy to answer any questions if you have any. Thank you.